There is motion all around you, and there are natural laws governing this motion. Natural laws that require the brakes to be applied as this train goes around a curve. And natural laws that require this biker to lean into his turn to avoid crashing. There are laws that cause people to feel pulled when going around a corner. There are laws that make us fall forward when a car suddenly stops. And if the car runs out of gas, there are laws that make it hard to get the car moving, and laws that make it hard to get it to stop. All of these examples have to do with the law of motion. Laws that were established over 300 years ago by an English scientist and mathematician named Isaac Newton. This videotape will present material about Newton's 3 laws of motion. During the tape, there will be 4 Stop the Tape sections where you will be asked to answer questions on your viewer's observation sheet. When you see this sign, you should stop the tape and do as instructed. So, let's begin. Newton lived at a time long before cars, planes, and speedy forms of transportation and motion. And yet, he was able to observe the motion of objects of his day and develop from those observations the 3 basic laws of motion. His laws describe how all objects move. Newton's first law has to do with objects at rest and objects that are moving. He noticed that objects at rest stayed that way until something came along to move them. He also noticed that objects that were moving continued to move in a straight path unless something slowed them down and stopped them. Newton called this tendency of an object at rest to stay at rest and an object in motion to continue moving inertia. You must overcome inertia to start an object moving. And you must overcome inertia to slow down and stop an object that is moving. So Newton's first law of motion states that if no unbalanced force acts on a moving object, the object will continue moving at the same speed and in the same direction. And if the object is not moving and at rest, it will remain at rest until an outside force acts on it. In simplified form, it means things keep doing what they were doing. Objects that are stopped will stay stopped, and objects that are moving will continue to move at the same speed and in the same direction unless acted upon by an outside force. A spacecraft will continue moving through space at a constant speed and in a straight path without the need for engines. Once the craft is away from the atmosphere and gravitational pull of Earth, the engines can be turned off. Because there is little matter in the vacuum or emptiness of space, there is nothing to slow the vehicle down. It will continue at a constant speed and in a straight path. If the engine is fired again, the craft will be able to change speed and direction. On Earth, objects are affected by outside forces that slow them down and eventually stop them. Even on very slippery surfaces such as ice, objects will be slowed to a stop. Friction is the force that slows things down. Friction occurs when 2 objects rub together or try to slide past each other. Friction between the surfaces of the puck and the ice causes the puck to slow down and stop. Stop the tape now and answer questions 1 and 2 on your observation sheet. Question 1 asks you to rub your hands quickly together. You should have found that within seconds your palms became warm, even hot. One of the effects of friction is heat. Next time you go for a ride in a car or on your bike, feel the tires after you have stopped. The heat you feel is from friction. The second question asks you to look at the soles of your shoes. What you should have discovered was that a wearing down of the sole has occurred. Where once new, clean treads existed, you probably have worn surfaces. So another effect of friction is to wear things down. Look at car and bike tires, and you'll see evidence of wear and tear brought on by friction. So friction slows an object until it stops, produces heat, and wears the object down. To avoid friction, we use lubricants such as engine oil to make the engine surfaces slide easily past each other and cut down on heat and wear from friction. If we didn't have friction, things would be very crazy. For instance, the process of walking or running occurs because of friction between our feet and the ground. Without friction, a person at rest or at a standstill could not get moving. And objects that were moving would not be able to stop because they require friction between their surface and the ground to slow down. Here is a computer game for playing billiards. We can turn the friction level to a setting that is very close to 0. Watch what happens when the cue ball is hit into the other balls. All this motion and uncontrolled activity is a result of very little friction. The inertia of the balls keeps them moving in straight paths until they strike other balls or the sides of the pool table. We can't expect the same thing to happen in real life. Here is an illustration of inertia. This tablecloth is loaded with inexpensive china and glasses of water. Now watch as we quickly pull on the tablecloth. Inertia is responsible for holding the china and glassware in place. Now, you may not want to try this at home, so here is a version of that same experiment, but only a coin, a piece of cardboard, and a glass are required. Your mother's good china is saved. Here is another demonstration of inertia. A large rock is supported on this person's head. A piece of wood is placed on top, and a friend proceeds to drive a nail into the wood. Why no headache? Inertia. The rock doesn't want to budge. It absorbs the force of the hammer blows, and the person underneath survives. Now, let's consider the inertia of an object that is moving. When you're riding in a car and the vehicle goes around a corner, you feel like you're sliding off to one side. Actually, your body wants to continue going straight as the vehicle turns. We can demonstrate this with this ball and handcart. When the cart turns, the ball rolls off. Now let's step back and see what is really happening. When the cart turns, the ball continues to travel in a straight line. So when you're in a car and it suddenly turns, your body really wants to continue in a straight line. A spinning gyroscope will resist changing its starting position. It can be balanced on a string or small stand. In the weightless environment of space, the gyroscope works even better. So, inertia explains many common everyday situations. Now, let's look at Newton's second law of motion. This tells what happens to a moving object when a force is applied to it. This batter will strike the pitched ball and change the ball's direction. Oops! I mean, he will try to strike the ball and change its direction. Well, if he does make contact with the ball, the force of his swing and the bat that he is holding will accelerate the ball in a different direction. There, the ball is hit. It travels in the direction that the force is applied. If the batter hits it straight on, the ball will change direction and travel in the direction of the swing. How much it accelerates depends on the strength of the force and the mass of the ball. Mass is not the same as an object's weight. Weight is a measure of gravitational pull, and it changes as an object gets farther from the earth. Mass doesn't change. It is a measure of an object's inertia. The greater the mass, the harder it is to get the object moving, or to stop the object from moving. As we add more and more mass to this cart, the amount of force required to get the cart going increases. Newton found that the more mass an object has, the greater the force must be to change the object's motion. That's why we don't play softball with a shot put. There would never be a home run, and beanballs would be lethal. So, the second law of motion says that the change of motion of an object depends on the size of the force and the mass of the object. The greater the force, the greater the acceleration. The greater the mass, the smaller the acceleration. It is harder to stop a train than it is a car, even when the car is moving faster. That's because the train has a greater mass than the car, and it will require a greater force to slow it down. We say the train has greater momentum. Momentum is the strength of an object's motion. The more mass an object has, the greater its momentum. Momentum is determined by multiplying the mass of a moving object by its speed. The faster an object goes, the greater its momentum. Now we come to Newton's third law of motion. For every action, there is an equal and opposite reaction. A rocket uses that principle to blast off of the ground. As the fuel is burned and gases shoot out the nozzle of the rocket engine, an opposite and equal force moves the rocket upward. Here is a cart with a heavy metal weight and a strong rubber band pulled tight and ready for release. What do you think will happen when the string that holds the rubber band is burned through? Stop the tape and answer question 3 on your observation sheet. As you may have guessed, when the string broke, the rubber band caused the weight to fly off in one direction, and the cart went zooming in the opposite direction. When someone shoots a rifle, they feel the kick of Newton's third law. The bullet goes out the muzzle, and the rifle is kicked into the person's shoulder. These rocket cars are powered by CO2 cartridges, that is, carbon dioxide gas. When the nail punctures the end of the CO2 capsule, carbon dioxide gas escapes out the back. The car goes zooming forward. It moves in an opposite direction to the escaping gas. Roller coasters and other amusement park rides are based on the laws of motion. The wild turns are designed to take advantage of inertia and another force called centripetal force. We'll show an example of centripetal force using this flat piece of wood and this glass. The glass will stay on the piece of wood while spinning around and around. Even when overhead, the glass stays in place on the board platform. How would you explain why the glass remains on the board? Stop the tape and answer question 4 on your observation sheet. The glass and board want to travel out away from the person. They want to travel in a straight line, and if we let go of the rope, that's what will happen. The board and glass will fly off in a straight path. So, the rope is holding the board and glass inward and in a circle. The glass, because of inertia, wants to fly away, but the bottom of the board is sturdy and holds the glass in place. The force required by a person to hold the rope inward and to resist the outward straight-ahead motion of the board and glass is called centripetal force. If you don't want to risk breaking a drinking glass, try this. Bend a coat hanger as shown, then hold it with one finger as demonstrated. Carefully place a coin on the tip of the hanger hook and begin to spin. It may take a few tries, but it's possible to spin that coin with grace and ease. You have experienced centripetal force and inertia if you've ever been on amusement rides like these. A roller coaster ride can carry you upside down or through a series of loops because of inertia and centripetal force. Today we looked at the 3 laws of motion established by Isaac Newton back in the 1600s. Newton's first law of motion states that an object at rest will stay at rest, and a moving object will keep moving at the same speed and in the same direction unless an outside force acts upon it. His second law of motion states that an object accelerates when a force acts upon it. The stronger the force, the greater the acceleration. The greater the mass of the object, the larger the force must be to accelerate the object. And Newton's third law says that for every action, there is an equal and opposite reaction. While talking about the laws of motion, we have also discussed friction, which has a dramatic effect on moving objects. Friction occurs when 2 objects rub together. It slows the objects down and produces heat and wear. We also talked about centripetal force, which causes an object to move in a curved path. So there are examples of Newton's laws all around us, and we use and obey these laws every day in the things we do and the movements we make.